And yeah, I mean, so yeah, another thing. So is it okay if I take an extra class tomorrow? Same time, let's say 11 to 12, just to cover up. Okay.
Yes.
Does anyone have a problem with that? Anyway, the recording will be there. So just for so that there is a live interaction, so that the people can join in. I'll take an extra class tomorrow from 11 to 12. Okay. And these internet issues, like we are living in a not really a first world country, so we have to really rely on the internet provider, and it's not that if they the thing goes bad and we can sue them or something like that. So they don't care much either. So I mean, this can happen to anybody, and I would hope from you guys also to have some understanding that, okay, I mean, so if you get logged off, but it doesn't show up, but I'm responsible for the class. So if my internet goes bad, then like the responsibility is higher. So that's why I also feel bad when that happens. So please, be a bit understanding and not be too harsh. That's all I would say. Okay, good.
Uh, Excuse me, sir.
Yeah.
Can you please upload the lecture slides as well, like the notes that you make?
Pratik, no. So we had talked about this. So this keeps coming up again and again. So these are not really lecture slides, right? So these are something like like we do in a classroom, like I write on the blackboard. Okay. So the lecture is available. You can have a relook at it. But these are not very formally written notes. Let's say I draw very random things and so on. So if somebody wants to look at these also, they can go back to the lecture and see. But these are not really I don't see how they are going to be in that way helpful. You are encouraged to make notes while I teach, and your own notes will be much more useful to you. And I don't think so. This is we have discussed this, so I will not be doing that.
Okay,
Okay.
okay, that's fine.
Yeah. Thank you, Pratik.
Excuse me,
Uh,
sir.
yeah.
Sir, could you please tell when the assignments will be uploaded?
Yeah,
Means,
thanks for asking that. So I'm thinking of sending the first assignment before 1st of September. Okay, and generally the time will be first couple of assignments, maybe time will be 10 days, and later if the assignments get harder, it will be about 2 weeks. Okay, so there will be 3 to 4.
sir, will it be related to coding or something which we need to write?
No, again, so Rishabh, I think we had discussed these things also, that they are just going to be theoretical assignments. You'll need to design an algorithm, or whatever questions are answered, it's going to be theoretical. It's not going to be coding related. Okay. Any other questions? Okay, good. So let's go ahead, and so I'll quickly, whatever I was trying yesterday, I'll just quickly go through that. So in the last lecture, I mean not yesterday, before that, so what we had seen interval scheduling, right? And there are a few related problems, right? So what are the related problems which are related to interval scheduling? So first thing is that the set of intervals which are there. So first is the intervals might not be known a priori, right, to the algorithm. That maybe the requests are coming, one by one, and you don't really know from beforehand what these are. There can be some values attached to the intervals or jobs, and the task is to maximize the value rather than just accommodating maximum number of requests. So this is the first one, is the realm of online algorithms. So that is a huge field by itself, and it's growing more and more, where like, so you get a stream of data instead of like you get all the data at once, and then you have to keep, like, if you have an online application, like, browser application and so on, so many users are logging in, you don't know what the behavior of the users or what the behavior is going to be in the future, and you have to still make the decisions at the moment that, okay, what I'm going to do right now. And the second one is like, okay, not all jobs are created equal. So some jobs have, higher value and you want to maximize the value and so on. Another problem is, let's say that many jobs want to schedule all of them, but want to minimize resources. So again, I thought this part I was able to at least, I was able to define the problem that, yeah, we had seen that, okay, all these, so these are the jobs that have come and so on. So the minimum number of resources required is going to be the depth. I had defined depth, right? Here is equal to 4, which is the maximum number of intervals intersecting at any given point, and depth is a lower bound for the number of resources required. And what I said yesterday, or is that actually the jobs can be scheduled with number of resources equal to depth. Okay, and that, like, the simple algorithm was, which I just like hinted at. I did not really describe it in detail or whatever. That you sort the, like, all the intervals by their whatever start time, and then the first job you assign to the first resource available, the next job to the next resource available. So you give it 1, 2, 3, 4, and then, okay, nothing is starting here actually. This one. Now you see that 1 and 2 have become like free, so you can give it 1, you can give this one 2, and so on. So you can just, like, go like this and keep assigning resources, and you will never use resources more than what is the depth. So this also gives an algorithm that does it in the optimum way. Oh, and why is it optimum? Because this is a lower bound also. The depth is a lower bound. So this you can read from the book, and this is a very simple algorithm and very simple analysis. So I'm not going to get into detail of this problem, but just to know that, it's, another variant of the scheduling problem, and you can solve it using greedy algorithms. Okay, good. So the problem that we'll be looking at today is scheduling to, which is another variant actually, minimize lateness. Okay, good. So what is the input here? Input is set of jobs. Again, let's say 1 to n. Okay. And for each job I, we have, now instead of the start and the end time, we have the length or the time period, let's say Ti, and the deadline, Di. Okay. So this is what we have. So now what the algorithm, so what does the deadline mean? That the job ideally wants to finish before the deadline, right? So what the algorithm needs to do? Algorithm needs to assign each job an SI and FI, which is like, which is basically FI is equal to SI plus TI. right? Right. So for all I, it needs to do. So what does it mean? That okay, jobs are coming. They are not saying when are they going to start. They are not saying when are they going to finish. But they are saying that okay, my length is this much, and I would like to finish before this deadline. The deadline is DI, right? Okay. So now suppose we want to schedule all jobs, and it's not possible that we can schedule all of them uh, in without crossing the deadline. So maybe the jobs can be late. Okay. So let's define this lateness of a job and call it Li. Okay, equal to minimum of 0 comma Fi minus Di. So what does this mean? I mean, where this just seems like, okay, I'm using minimum and there are these two quantities and so on, but actually it's quite simple. What it is trying to say that, okay, suppose a job got late. So it did not finish by DI, actually it finished later. Then this is its lateness. And if it finishes before, then this quantity is going to be negative, so we just take 0. So either it is 0 or it is, this difference between Fi and Di. Okay, so that is the lateness of a job, right? And what is the output that we want to have from the algorithm? So this is a schedule, right? When the algorithm assigns every job an SI and a TI, then that is a schedule. So
Say it should be maximum of 0 or minimum of 0 comma fi minus di.
sorry.
It should be maximum of 0 comma fi minus di.
Yeah, wait, you are right. Should be maximum of. Thank you. Yeah. So either it is 0 or this number. So whenever this number is positive, of course we take that number. Whenever this number is negative, we take 0. Thank you for pointing it out. Okay. So good. Yeah. So now what is the output of the algorithm that is expected? A schedule. So this is a schedule, right, where the algorithm is assigning Si and Fi for every job, where Fi gets fixed, Si gets fixed. So what is the output? Output is a schedule that minimizes the maximum lateness among all jobs. That is minimizes, sorry, max overall I, Li, right? So is the problem clear? Or if there is any confusion about uh, the problem statement, then please ask now. Okay. So all right. So I guess the problem is clear then. Or please, let's take a few more seconds to think about it. What the problem is?
Like in this problem, we have to minimize the total lateness that happens, right?
No, no, the max of the lateness. So we are not taking sum, we are taking the max. Okay. Any other doubt, question? Okay, good. So let's now again look at some possible approaches that can happen, right? So one very trivial attempt can be that okay. like schedule the shortest jobs first. So that they don't get late or whatever, right? This is one way. So that is basically sort TIs and schedule according to in order, right? So yeah, so can someone give an example or tell why this will not work? So let's say that this will not work.
The longest job has the first deadline and so on. Like
So the longest job has the first deadline. I mean, that is also actually not necessary that that is the only. In fact, the longest job. So another thing you can assume here that DI is greater than or equal to TI. I mean, it would not make sense otherwise to look for the deadline. So generally, then the longer job will have a later deadline because it's longer, right? But even otherwise, so let's look at So yeah, can somebody think of any other counterexample? I mean, I can anyway. But yeah, I mean that is true actually. That so suppose shorter job has T1 is equal to 2, and I just meant that this should be there, but anyway. So suppose D1 is equal to 12. So this counterexample is actually correct. That what you were saying, and T2 is equal to 10, and let's say T2 is equal to 10, right? So now if you schedule the shorter job first, then what is the lateness? Suppose schedule T1 first. Then what is L1? L1 is 0. What is L2?
two.
L2 is equal to 2. Why? Because then this job will finish at T is equal to 12. Right? And that, what is the deadline? Deadline is 10. So the lateness will be 2. And while if you schedule it the other way around, then the lateness will be, so if we schedule T2 first, then L1 is equal to 0 because this will finish at 12, and L2 is equal to 0 because this will finish at 10. Right? So the maximum is 0. Here the max is 2. So this one doesn't work. So fine. So this might feel like, okay, why are we uh, just looking at the duration of the job while we have a deadline also? So I'm sorry. Yeah. So, so why just look at just one aspect of, since we have these two quantities, and we were just looking at one quantity, which is T1, and designing the algorithm with that. Somebody can say that. So let's look at both these quantities, and let's say that okay. So take the difference Ti minus Ti and schedule jobs according to that. And this sort of makes sense, right? Why? Because this says that okay, these jobs don't have much leeway. If if their DI minus TI is very less, then the, the leeway that they have is very short. So we should be scheduling them first. The jobs which have larger leeway, maybe we can schedule them later, and they will still be fine. They will not get that much late. Right? So this might, seem like a plausible or, algorithm. But this also doesn't work. So again, can somebody guess why this would not work? Or any, again, like, in the earlier one, that shorter job has later deadline. That was one thing that we came up with. So here, what can be the problem or why this might not work? Okay, so I already said that this will not work.
So in the previous example, if we take T1 equals to 2 and L2 equals to 4,
Yeah,
T1 equals to 2 and D1 equals to 4.
exactly. So let's say T1 is equal to 2 and D1 is equal to 4, and let's say T2 is equal to 10 and D2 is equal to 10, right? So let's look at the two cases. First case is, so what is the difference? Difference here is 0, difference here is 2. So you will be scheduling this first. So schedule 2 first, right? So then what do we get? L1 is equal to, so if you schedule, what will be L1 if you schedule 2 first?
So 0.
L1 is equal, no. Why? You're scheduling 2 first, the job 2. So jobs are like, 1, 2. So this is job 1, this is job 2.
8.
Yeah, L1 is equal to 8. Why? Because this will finish at, so you have first 10 seconds for job 2 and then 2 seconds for job 1. So they finish at 12 while the deadline is 4. So L1 is equal to 8 and L2 is equal to 0. Right? So max is 8. And if you schedule 1 first, then what is L1?
Zero.
0. What is L2?
2.
L2 is 2. So the max is 2. Right? So here the max is lower when we scheduled 1 first, and but due to our policy, what was our policy? That we look at DI minus TI, and DI minus TI is lower in the second job, so we should be scheduling 2 first, in which case we get the max to be more. So this is not a correct algorithm, right? Okay, cool. So let's look at actually, what works. And what works is just sort according to deadlines. That is DI. And schedule the job first, or, which has earliest deadline. Okay. So this is what we have. This is the algorithm that we have. So now, if you just look at it, this might not seem very intuitive that, okay, fine. When we were just looking at TIs, then you said that we are just looking at half the aspect of the problem, and we do not actually look at the full problem which is there, all the data that is there. Then when we looked at both, we didn't succeed. And now again, we are looking at only one aspect of the problem, which is DI. And now you're saying that this works. But that's what, things might be counterintuitive, but if they work, they work. And then you prove that they work. And that's how you go about things, right? So now to show that this algorithm actually works, we will, uh, try to make the algorithm more precise, and then try to argue about it and so on. So let's some, like, just some assumptions or notations. So first is that we will assume, so at least the algorithm is clear, right? That just sort the jobs according to their deadline. and just run them in order of deadline. Okay, so we will assume that the list is sorted. The jobs are already sorted according to deadline. This you can just relabel them, and this you can achieve after sorting. So D1 is less than or equal to D2 and so on, less than or equal to Dm if there are n jobs. Okay, and let S will be the starting time, or yeah, S be the starting time. Like the first time you can allot is S, right? Okay, good. So that means what is our algorithm going to do? S1 is equal to S, F1 is equal to S plus F1, sorry, S plus T1. Then S2 is equal to S plus T2, F2 is equal to whatever, and so on. So let's write this as an algorithm. And the algorithm is very simple. So first step is order the jobs in order of deadlines that we have already assumed, but let's since we are now writing the algorithm, and let the order be like D1, D2, Dn. Now let's put F is equal to S, which is the finish time of the current job or whatever job we have assigned till now. And now for I is equal to 1 to n, what do? We put starting time of the job as the current thing that we have, and the finish time of the job as F plus Ti, right? And then what we do, F is equal to F plus Ti. We increase this that, and then we end the for loop. And finally, we just return. What do we return? We return the SITs for all I in, right? So is the algorithm clear? Any questions about the algorithm? No? Okay. So I mean, the algorithm is very simple actually, but if there is still any doubt, there can be, if I've not been able to. Why we sorted Fi if we don't want to return it? Did we sort Fi? Sorry, I didn't get the question.
Sir, we'll be returning SI and FI, right? And
Oh,
not
yes,
TI.
yes, yes. Sorry. Yeah. Good. Thank you. Of course, SI and FI. We return the start time and finish time for every job. Thank you. So, Mihir, does that answer your question? We return SI and FI.
Yes, sir. Like I was asking why we are storing, not sorting. So.
Okay, okay. Sorry. Yeah, I didn't read it correctly. Cool. Thank you. Yeah, so we are returning it because for every job, that can be inferred also, but let's say that we return FI also. Okay. Any other question? Okay, so Mrityunjay, you had a question earlier which I had missed. Did I answer that, or shouldn't it be max of 0 and that thing? Okay, all right, good, thank you. Good. Okay, so yeah, so the algorithm is clear, I guess. Okay, so let's now get into the correctness of the algorithm. So the correctness will involve like, certain steps. And this is where we'll make use of the exchange argument, which was the second technique that that I had told you that, okay, we'll be using these two techniques. One is the staying ahead and the second one is the exchange argument. So today we'll be looking at the exchange argument technique. Okay. But before that, let's just like, state some very basic and simple things. That lemma 1 just says that there is an optimal scheduling. So what is an optimal scheduling? Optimal scheduling that minimizes the max of the lateness, right? With no gaps. Okay. And the proof of this is like, very obvious that you can just shift everything. So I'm not going to do this one. If there is gap, of course, this it's not optimum. Whatever you are doing later, you just shift it back, and you'll get, the lateness can only decrease by that. I mean, if at all lateness changes, then it can only decrease. Okay, good. So this is like very simple, but okay. So now suppose, so let this schedule be A. Okay, the output. We want to show that A is optimal. A is optimal. Or A is an optimal schedule, like, if you want to be more precise. Okay, good.
Excuse me, sir.
Yeah.
Sir, like while discussing the algorithm, should we not have mentioned, like, should we not have considered the case of ties as well? Like, if the deadline for.
Yeah, good question. So let's say that we do that arbitrarily. Okay. So we break the ties.
So will arbitrarily work correctly?
We'll see that. We'll come to that. Okay.
Okay, sir.
Yeah. So let's assume for now that the algorithm breaks the ties arbitrarily, and we'll see whether arbitrarily works correctly. Okay. Good. Good question. Actually, that is a point to consider. So here you can just say that, if DIs are same, put them in any order. So basically you can have just a non-decreasing sequence and you are fine. Any non-decreasing sequence is fine. Okay, good. So let's come to this, that we want to show that A is optimal, right? Okay, so this is where, so yeah, so the algorithm might output these different things. If there are like, different jobs with the same deadline, the algorithm will or can arrange them in different orders, in different, like, but we'll show that, okay, it does not really matter. So we'll make use of this thing called exchange argument. So before that, let's define a few things. Okay. So yeah, so first thing is that as Shaman was saying, that algorithm might output different schedules if there are many jobs with same deadline, right? Okay, but there is this one thing that the algorithm will never do. So let's call this an inversion, okay? So the algorithm never schedules a job I before job J, or let's say a job J before job I, if Di is less than Dj. Right? So this is definitely the algorithm never does. Right? If the deadline of I is strictly less than deadline of J, then the algorithm will never schedule job J before the job I. So if such a thing happens in a schedule, we say that schedule has an inversion. Okay, so this is what we know, and what we know that the A, the output, A does not have any inversions by definition or by the run of the algorithms, right? Any doubt about this till now? Okay. So now let's write a lemma 2 which will clear Shravan's doubt that all schedules with no inversions and no gap, like there is no gap between two jobs, have the same maximum lateness. Okay. So will this, if we prove this, will that clear it out, Shravan?
Yeah, yes, sir. Yeah.
Yeah, good. So right, let's prove this, and this is actually not going to be very hard. So all you need to care about is, that you have one deadline, which is, so let's say that there are some jobs like, without loss of generality, let's say that 1, 2, 3 to K, all of them have DI is equal to whatever, something, some T star for all I in K. Okay. So this is the deadline, which is same for these K jobs. So what did I say? That it does not matter how they get scheduled. So if all of them get scheduled before, if they finish before, then the lateness of all of them is 0. It does not matter, right? So also they will start at some point. So it does not matter how they get scheduled, but the start time and the finish time is going to be the same. So let's call them S star and F star, right? Is that clear? That since they all have the same deadline, their relative orderings might inside might change, but the start time and finish time is going to be the same of all of them. So this is like, here some of them are scheduled here, whatever, right? So they have the same deadline. Their time periods can be different. TIs can be different. So they might not have same length. Some can be very small, some can be very large. But what is the lateness? So let's look at so let's say that they are getting late. So let's say that F star is much, much later. Okay. And this is the D star, which is the deadline for all of them. So, okay. So now, and this was S star somewhere, or it can be anywhere. So in that case, what is the lateness? What is the maximum lateness? Is of the job that was scheduled the last. And what is the maximum lateness? This much is F star minus T star. Right now, even if you like change the ordering, still there will be a job that will finish at F star and its lateness is going to be F star minus T star. And that is going to be the maximum lateness. So whatever job is at the end, it will finish at F star, and that is going to have the maximum lateness among these. I'm not saying for the whole scheduling. Among these, it is going to have the maximum lateness, and that is not going to change if we change the relative ordering of these guys. Okay, so the maximum lateness is going to be the same, does not depend on ordering. Lateness of jobs in 1 to k, depend on ordering, and the lateness of every other job remains the same. So maximum lateness also remains the same. Same if you order these differently. Is that clear?
Sir, I could not understand why will the finishing time be same for all, because
Not for all. Finishing time, as in finishing time of this whole batch, it will not be the same. So this F star is not the finishing time of all. S star, so you have some ordering, and in that ordering, you choose any ordering. You first schedule some job, then you schedule some job, then you schedule some job, and so on. But the total length of these jobs is going to be the same,
right.
right? So if you start at S star, it does not matter in what order you schedule them, they will finish at F star. So what is F star? F star is equal to S star plus summation of TID, I in K.
Right.
Right? So that will what will give us F star.
And then why are we considering what are we considering D star to be? I could not get it.
T star is the common deadline of
Sir,
all of the jobs.
so are
So
we assuming all the jobs have the same common deadline?
not all the jobs, 1 to K,
Okay, got
some
it.
subset of jobs.
Got it.
Okay, so only where the some jobs have the common deadline. That's where their relative ordering can differ, and we assume them to be some subset of the jobs 1 to K.
Got it. Thank you.
Okay. Any other question?
So do we actually need to prove this lemma? Like once we do the exchange argument, wouldn't it be apparent?
Wouldn't it be apparent? So while doing the exchange argument, we want to avoid this thing, and uh, I mean, exchange will not happen in this way. That will touch the things with common deadline. So yeah, it's at least the way I'm going to do the exchange argument is not going to be this. So let's look at the exchange argument, and then maybe we can come back to this question, because we will be we'll have to hurry up a little bit. So, but I hope the lemma is clear to everyone that what we were trying to do. So now what we want to say, there is an optimal schedule with no gaps and no inversions. Okay, so this is what we want to show. And if we show this lemma, then we are done basically. Right? Because if there is an optimum schedule with no gaps and no inversions, because then we have shown that, okay, all the schedules with no gaps and no inversions have the same a schedule with no gaps and no inversions. So our schedule is A is optimal, right? So convince yourself, that showing this lemma actually, so it requires A, no gaps, no inversions, that we have seen. So A is optimal uh, because of lemma 2, because all the optimal ones. Okay, and A has no gaps because of this thing. Yeah, because of construction of A. Okay, so this is just fine. So all right. So A is optimal because of lemma 2, because all the schedules which have no gaps and no inversions have the same maximum lateness. All right. So let's show now lemma 3, and then we'll be done. Okay. So let O be an optimum schedule. So now we'll be looking at the exchange argument. So what we want to do now, we want to change O slowly to get to A without making it worse. So we'll just, tweak O slightly to, go towards A. And all the while we'll maintain that, we are not making it worse. The maximum lateness does not increase. Okay? Good. So now, so if O does not have inversion, then we are done, because then we have shown that every maximum schedule, every optimum schedule that does not have inversion has the, and gap is, having same maximum latency. So if O does not have any inversion, then we are done, because then A will have the same maximum lateness, right? Okay. So suppose now O has inversion. So if O does not have inversion, nothing to show because of lemma 3, lemma 2, right? Now suppose O has inversion. So now if O has an inversion, then there will be some place where, there is some job I, okay? So, and there is some Di and Dj, such that J is scheduled before, right before I, actually. Okay, and why does that happen? Because, so basically, whenever it has an inversion, that means there is a Di and Dj, such that there can be gap, actually, that J is scheduled before I. But then there will be some place where this number will go down. So the number will increase of the jobs. So 1, 2, 3. So if you have some higher number here, let's say 15, and you have a number here 6, then there will be somewhere where this will decrease in one step. Okay. So if it keeps on increasing, then it will decrease here. Otherwise, it will decrease at some place in the middle. So there will be two consecutive jobs such that there will be an inversion there. Okay. So if there is an inversion, there is a O has an inversion, it has an immediate inversion, let's say. Good. Okay. So now what is the claim? If we switch the order of J and I, the maximum lateness does not change. Okay. So how do we show
does
that?
Not
Yeah.
change or does not increase?
Yeah, you're right. So does not change. If it does not increase, then it will not change also. I mean, it's fine. Maximum lateness. But yeah, just to be precise, we can say. Yeah, actually, oh, it can change. You are right. It can decrease. Yeah, thank you. Yeah. It does not increase. That's all we want to show. So it can decrease if at all, but it does not increase. Okay. So let's just quickly, look at the proof that why it does not. So earlier, so let's say the earlier lateness was Li1 and Lj1, and now the lateness is Li2 and Lj2 in the new schedule, right? So now the thing is that if you schedule I first, so Okay, let's just, to make it slightly, let's say that I is shorter, just so that, people don't think that it is. So now we scheduled I first in the other schedule, and then we scheduled J, right? So now, if you look at it, the lateness of I, if anything, it decreases, right? So the lateness of I does not increase. But what about lateness of J? That can increase, right? But we want to show that lateness of J, that is lateness of J in 2, is less than or equal to lateness of I in 1. And if we can show that, then we are good, right? Because then how can, the maximum lateness increase? Because Li was already bigger than. And what is the lateness of J in 2? Now suppose the finish time of these was some F, okay? And here also it's the same F, right? So, I mean, the deadlines can be before, like, it might not be later, because suppose it is non-zero, the lateness. So, what is Li1? Li1 is F minus Di. And what is Lj2 is equal to F minus Dj. And we know that Dj is greater than or equal to Di, or strictly greater than Di. So then we get this, that Lj2 is less than or equal to Li1, right? So that just means that since the deadline of DJ was later, if we finish now, DJ later, then like still its lateness will not go beyond the lateness of whatever the lateness of I was earlier, right? So this basically,
Um,
yeah,
Excuse me, sir.
yeah.
So like as someone said before, so like we did not really have to prove lemma 2, right? We could have worked with like greater than equal to sign as well.
Where?
Like if di is equal to
Okay, fine.
dj,
Yeah,
li1
yeah.
will be greater than equal to lj2.
Okay. So you are saying that, okay, so here we don't have to, but this we are doing just for inversions, and then we, we needed that, okay, we are making some progress in some sense, because now it will come that, because you can keep shifting the equal deadline ones and you are not making any progress then. So from O, we want to go to A, and we need to be making some progress for that. That is why we were showing this lemma in the sense of inversions.
Yeah, okay, sir. Yeah.
Yeah, you get the subtlety. I mean, of course, you can do that in some way. There might be, and it will not be too different, but okay. Yeah. Okay, so yeah, so now we'll say that, okay, we have uh, a schedule that has one inversion less. And total number of inversions can be n choose 2. So this process stops after n choose 2 steps. Okay, and then we get to finally no inversion and no gap. And while the maximum lateness does not increase at every step, so we have shown lemma 3, and hence we have shown the correctness of our algorithm. Okay, any question?
So yeah, I have
Yeah.
trouble. How did we get Li1 and like L? Okay, wait a second.
Yeah, here.
Okay, so
So
did we
what?
assume that Li will be responsible for the maximum lateness, or J will be responsible for the maximum lateness?
No, we didn't. We didn't assume that. All we are going to show is that, the maximum lateness does not go up, okay? So maybe somebody else is responsible and then we are good anyway, right? So suppose, okay, let's just look at case by case. If LJ1 was responsible, okay? Okay, no, let's first look at if, um, yeah, if Li1 was responsible, then
So like when we have an inversion, I will have to be responsible. J cannot be.
yeah. So in the second one, yeah, exactly. In the second one, if anything, so in the first one, J is, the J's lateness is going to go down in the second one. So we look at all the set of lateness in the first one and look at, okay, can anyone go up from the maximum lateness? So let the maximum lateness of first one be like, M1, okay? And the maximum lateness of this be M2. The second one be M2, right? So now M1, we know that, so we want to show that M2 is less than or equal to M1. Right? Okay. So now if M1 was because of J or I, right? Then if M1 is equal to Li1, let's say, then in M2, Li1, like, this goes down. If M2 also is Li1, Li2, then Li2 is less than or equal to M1 anyway. So we are good. So let's do this. M2 has two possibilities of maximum. If it is Li2 or it has Lj2, right? These two are the only ones that are changing, and nothing else is changing in M2. So these two are the ones that can be examined. So if it is Li2, then Li2 has only decreased from Li1, right? So that cannot really be responsible for the lateness, or the lateness cannot go up. Now, if it is Lj2, then Lj2 is less than or equal to Li1 and is less than or equal to M1, right?
So how did we show that Li2 will always be less than Li1?
We didn't, how did we show that Li2 is less than or equal to Li1? Because the deadline remains the same of I, and I is now getting scheduled before. So it will finish before than whenever it was being finished earlier. Okay? Does it answer? Mani?
Yeah, sir. I'm just a
You were
bit
asking that.
confused. Yeah, yes, sir. I'll just
Okay,
go
so
with
what we
once
did,
again.
yeah, so just like let me try once more. And so what we did here is we scheduled I before J, right? Earlier J was getting scheduled before I. Now since the deadline of I was before J, we scheduled I before J. So deadlines remain the same. Now the finishing time of I can only decrease. So because of that, the lateness of I can only decrease.
Okay, so
Okay. Any other question? So yeah, I mean, this is the equation which, like, if you want to look at that, in this case, what happens? And Li2 is less than or equal to Li1. So these two are the things that should convince you then. And this is less than or equal to M. Okay. So also, I mean, so this is done actually, and running time is just order and log n, because you just sort them initially, and then after that, you're just assigning, you're just running this loop once, wherever the algorithm is. Yeah, you're just running this loop once, so this will take order n time. The sorting will take order n log n time. Okay, so the running time is order and log n. So this is the exchange argument, and of course you can have a look at it later. But this is the basic thing that okay, we are exchanging, and then I goes below, and yeah, the this thing of I can only decrease, lateness of I can only decrease. Lateness of J can increase, but it cannot increase more than what was lateness of I earlier itself, because the deadline of I is before the deadline of J. Okay. So yeah, any questions? Quick questions?
Sir, here actually we can combine lemma 2 and lemma 3 by just modifying lemma 3 a little bit. Here we are assuming dj is greater than di, right? If we just prove dj is greater than equal to di, then
I mean,
lemma 2 is
Shravan
not required.
suggested the same thing. Shravan suggested the same thing, but we want some notion of progress here.
Okay.
Because otherwise we can keep exchanging and we will never reach, like, if we just like, if we don't really have an inversion, then we, like, can keep exchanging the same pair, and we won't be able to do this, that after these many iterations actually we'll reach something which with no inversion. But yes, I mean, it can be combined. I'm not saying it cannot be combined, but like, you have to be like slightly more careful of things. That how you argue that, okay, how do you get from here to the, like, to the original or to one which has no inversion and so on. Anshuman?
Yeah. Yes.
Yeah. Okay. Any other? Okay, so we are over time anyway. So tomorrow we'll meet at 11 again, and I'll send an email also about that. Okay. So thank you all for coming. See you tomorrow.